All right, today we're diving into something pretty provocative. It's a new idea in physics called single-point theory, and it asks us to completely rethink the nature of reality, all starting with one simple, almost philosophical question.
Yeah, what if the fundamental particles that make up, everything, the electron lighting up your screen right now, the protons inside of you, what if they aren't little solid points at all? What if they're actually stable, self-sustaining vortices, these tiny, tiny tornadoes of energy just swirling away in the fabric of space itself? That, in a nutshell, is the wild idea behind single-point theory, or SPT.
And this isn't just a loose metaphor. The theory draws a really direct parallel. You see, a tornado holds itself together because of its internal structure, right? It has a certain persistence. Well, SPT suggests an electron does the exact same thing. Its incredible stability comes from what's called a topological charge. Now, you could think of that like a knot tied in the fabric of spacetime, a knot that just can't be easily untied. This means particles aren't permanent things, they're persistent patterns. A subtle but huge difference.
So, okay, if particles are vortices, you have to ask the obvious question, what are they vortices in? Where does all of this swirling begin? Well, SPT proposes a really radical starting point. It all comes from a single fundamental process. This right here is the proposed engine of all reality. They call it the primary cycle, and it's supposedly oscillating at a frequency that is, honestly, it's just mind-bendingly fast. We're talking about the time it takes light to cross the smallest possible distance in the universe. The idea is that everything we see and interact with, space, matter, you name it, is just a large-scale, emergent pattern that comes from this one incredibly frantic process. It's kind of like looking at the calm surface of the ocean, completely unaware of the trillions upon trillions of water molecules vibrating like crazy just beneath.
So, how in the world do you get a stable particle out of a simple cycle? Well, imagine this primary cycle creating a field of, say, vibrating threads. As all these threads oscillate, their phases can get tangled up with each other. And in the places where these tangles become stable, where they lock into a self-sustaining pattern, they create what physicists call a topological defect. And it's these defects, these persistent little knots in the process field, that we perceive as particles.
Okay, look, it's a beautiful idea. It's elegant. But beautiful ideas in physics are a dime a dozen if they can't do the math. Can this simple model actually reproduce the incredibly complex and precise results of modern physics? This is where the rubber meets the road. So let's put it to the test.
First up, the size of a hydrogen atom. This is a number we know incredibly well. And using its vortex model, SPT claims it can calculate this number, the Bohr radius, directly from its core principles. And this is the kicker. There are no fudge factors, no special adjustments needed. The theory says this value just emerges naturally from the dynamics of the model.
And get this, that same calculation doesn't just predict the atom's size, it also spits out the electron's speed. And the result? It's alpha, the fine structure constant, times the speed of light. That's exactly what standard quantum mechanics tells us it should be. So both the size of the orbit and the speed of the electron in that orbit seem to match up perfectly.
The theory also goes after something called the fine structure of hydrogen. This is a tiny, tiny split in the energy levels of the atom that was a massive, landmark success for Dirac's relativistic quantum theory. But SPT says, hold on, maybe it's not a relativistic effect at all. Maybe it's just geometry. The idea is that the electron vortex can lock into two slightly different but equally stable shapes, and that tiny difference in shape creates the energy split we observe.
Now this is where things get really fascinating, and maybe a little weird. SPT suggests this deep principle of stability isn't just for physics, it points to pure mathematics, to something called perfect numbers. Numbers like 6 or 28, whose divisors add up to the number itself. The theory argues these aren't just a cute mathematical curiosity, it claims they're signatures of the exact same kind of resonant harmony that makes an atom stable.
Look, explaining stuff we already know is one thing. That's important. But a real scientific theory has to stick its neck out. It has to make new predictions about things we don't know yet, predictions that can be tested and, crucially, that could be proven wrong. This is the moment of truth for single-point theory.
Okay, so here it is, the showdown. It all comes down to the Lamb shift, another one of these tiny energy shifts inside an atom. Our standard model, quantum electrodynamics, or QED, has a fantastic explanation for it. But SPT has a different one, and here's the key. For really, really heavy atoms, what we call high Z ions, the two theories predict different outcomes. As you can see here, QED's prediction scales one way, while SPT's prediction scales another way. This is not a subtle thing. This is a clear fork in the road, something you can actually go out and measure in a lab.
And this is the commitment. The people behind this theory have drawn a line in the sand. They are stating, with no ambiguity, that if experiments on these heavy ions don't show the deviation they predict, if the results match the standard model perfectly, then their theory is wrong. It's falsified. And frankly, that's what makes it real science. It's a willingness to be proven wrong.
So, what's next? Well, this theory isn't being presented as some finished, perfect masterpiece. Far from it. Instead, it's being put out there as an invitation. It's a framework for asking new questions and, more importantly, a call for collaboration, to really push its limits and see if it breaks.
This is basically a direct call out to the scientific community. Are you an atomic spectroscopist who can run those high Z ion experiments? Are you a mathematician who works on the kinds of equations that could put the stability of these vortices on a more rigorous footing? A physicist thinking about quantum gravity? I mean, the theory even proposes that its ideas about cohesion could be applied to complex biological systems like tumors. This is a hunt for critical partners, and yes, for skeptics to kick the tires. And in the end, it all comes back to this simple but really profound thought from the theory's originator, Damon Higgins. He didn't start with a mountain of equations. He started with a foundational what if. What if we've been thinking about the beginning of everything all wrong? It's just a great reminder that sometimes the biggest leaps in science come from a fresh look at our most basic assumptions.
So what do you think? Is this just a fascinating but ultimately wrong turn, a dead end? Or could it be a genuinely new path towards the holy grail of physics, unification? The theory's on the table, its predictions are testable, and the invitation has been sent. Now, it's up to the scientific community to decide what to do with it.